We will now continue our talk of exponential functions. Recall in the last example, we found that the amount of money owed on a $100,000 loan after t years with a 10% interest rate is given by the exponential function p of t equals t times 1.1 to the t. In general, an exponential function is a function of the form p of t equals p naught times a to the t, where p naught and a are constants, while the variable is t, our exponent, which is where they get their name exponential functions. It is worth noting that we can evaluate p of 0 to get p naught times a to the 0, which is just p naught because a to the 0 equals 1. So our constant p naught is simply p of 0. So what about the other constant, a? Let's come back to our example to understand a. We found the following data. When t is 0, p of 0 is 100,000. When t is 1, p of 1 is 110,000. p of 2 is 121,000. And p of 3 is 133,100. Let's compute the average rate of change on each time interval. From t equals 0 to t equals 1, the average rate of change is our change in p, 110,000 minus 100,000, over our change in t, 1 minus 0, which reduces to 10,000 over 1, which is simply 10,000. What about from t equals 1 to t equals 2? Here, our change in p is 121,000 minus 110,000 over our change in t, which is 2 minus 1. This simplifies down to 11,000 over 1, which is simply 11,000. Finally, on our last interval, from t equals 2 to t equals 3, our average rate of change is 133,100 minus 121,000 all over 3 minus 2, which simplifies down to 12,100. At this point, there's not a clear pattern. But what if we look at relative change? Our relative change from t equals 0 to t equals 1 can be found as our change in p over p, which is 110,000 minus 1,000 over 100,000, which simplifies to 10,000 over 100,000, or 0.1. Our relative change from t equals 1 to t equals 2 is 121,000 minus 11,000 over our original p on that time interval, which is 110,000. This simplifies down to 11,000 over 110,000, which is 0.1. Finally, from t equals 2 to t equals 3, our relative change is 133,100 minus 121,000, all divided by 121,000, which again simplifies down to 0.1. Here we do see a pattern. So what's the significance of 0.1? Well, we've found that our relative change is always 0.1. It's worth pointing out here that linear functions have the same rate of change between any 2 points, and exponential functions have the same relative change when we increase t by 1. For our function p of t equals 100,000 times 1.1 to the t, relative change is 0.1. In general, we can write a as 1 plus r, where r is our relative change. So we found for the exponential function p of t equal to p naught times a to the t, that p naught is p of 0, or our original amount, and a is 1 plus r, where r is our relative change. Exponential functions come in 2 varieties. If a is greater than 1, then r must be greater than 0, and we have positive relative change, so the exponential function is increasing. In this case, we say r is the exponential growth rate. On the other hand, if a is less than 1, then r must be negative, and we have negative relative change. So the exponential function is decreasing. In this case, we say r is the exponential decay rate. Let's look at the graph in each situation. If a is greater than 1 and r is positive, then our function is increasing. Notice that our y-intercept, or in this case our p-intercept, happens when t equals 0, so it happens at p of 0. In the other scenario, if a is less than 1 and we have exponential decay, then our function is decreasing. Again, our p-intercept happens when t is 0 at p of 0.